Section: Introduction and Related Work. In this section, we outline the stages involved in large video recommendation systems. First, we generate a short list of video candidates from a vast collection. Next, we use a multitask model to predict user behaviors, such as click-through rates and watch time, for these candidates. We then combine these predictions into a single ranking score to sort the candidates. After that, we apply additional logic to the ranking score to meet other goals, like ensuring diversity and considering interactions between items. Our focus is primarily on the ranking stage, where we aim to optimize long-term user satisfaction by combining user behavior predictions. Most current systems, like those from Meta, Pinterest, and Kuaishou, use a heuristic ranking function to merge these predictions. For instance, given user behavior predictions, the ranking can be calculated as a weighted sum of these predictions, where the weights are hyperparameters. These systems often use methods like Bayesian optimization to fine-tune the ranking function. However, as the number of hyperparameters increases, it becomes challenging to adjust objectives or add new input signals. To tackle this, we approach the problem as slate optimization, aiming to develop a general ranking function that maximizes long-term user satisfaction. We also review related work in slate optimization for long-term rewards. For example, the slate queue method uses reinforcement learning for slate optimization but overlooks how the position of a slate affects click probability. Other studies provide efficient algorithms for maximizing rewards under certain models but often assume that future rewards are zero if a user abandons a slate, which is not realistic for platforms with multiple recommendation systems. We recognize the importance of modeling the incremental value of a slate, especially since users may switch between different recommendation systems. Additionally, we address the stability of multi-objective optimization, which is crucial for maintaining consistent trade-offs among various objectives when changes are made to the algorithm. To overcome these limitations, we introduce the Learned Ranking Function (LRF) system. Our contributions include modeling user slate interactions as a click model, optimizing for long-term rewards while considering abandonment, and proposing a new constrained optimization algorithm to ensure stable trade-offs in multi-objective optimization. We demonstrate the implementation of the LRF on YouTube and present evaluation results. The remainder of the paper is structured as follows. We define the Markov decision process, MDP, for long-term rewards slate optimization, propose an optimization algorithm to address the MDP problem, and detail the deployment of the LRF on YouTube along with evaluation results. In our MDP formulation, we define the state space as a combination of user states and candidate videos. The action space consists of all possible rankings of these videos. We also establish the state transition probabilities and the reward function, which accounts for multiple types of rewards. Our goal is to maximize cumulative rewards for a primary objective while adhering to constraints on secondary objectives. Section Summary. In this section, we outline the stages of large video recommendation systems, focusing on the ranking stage where we aim to optimize long-term user satisfaction by combining user behavior predictions. We introduce our Learned Ranking Function (LRF) system, which addresses limitations in existing methods by modeling user slate interactions, optimizing for abandonment value, and ensuring stability in multi-objective optimization through a novel constrained algorithm. Section: Lift formulation with cascade click model. In this section, we define the expected cumulative reward, denoted as Q, when taking an action at a specific state and following a certain policy. We can express this as the immediate reward plus the expected future rewards. We will break down Q into functions that depend only on the user and the individual item. When we consider the position of a click, we can rewrite Q by factoring in the probabilities of different click positions. We note that the reward for a user abandoning the slate can be greater than 0. Since the total probability of all click positions equals 1, we can further express Q in terms of the expected rewards for different click positions. Next, we simplify the expected reward for a specific click position by assuming that future rewards depend solely on the item clicked. For a user and a set of items, we can express the expected reward for clicking an item as a user item function, while the expected reward for abandoning the slate can be represented as a user level function. We define the lift as the difference between the reward for clicking an item and the reward for abandoning the slate. We also simplify the probability of clicking an item by assuming a click model that allows users to abandon the slate, skip, or click on items. This leads us to a definition of the cascade click model, which describes user behavior in this context. Combining all these elements, we can express Q in a new form that includes the user abandoning the slate and the lift associated with clicking items. We refer to this as the lift formulation with the click model. A key question arises: how do we order items to maximize Q when we have a single objective? We find that, despite the complexity of the slate, we can solve this problem using a ranking function based on user-item interactions. The optimal ranking for a user involves ordering items based on a specific formula that considers the probabilities of clicking and abandoning, along with the lift associated with each item. Section Summary. In this section, we define the expected cumulative reward for a user interacting with items using a cascade click model, factoring it into user-item functions based on click positions. We derive a lift formulation that allows us to optimize item ordering to maximize rewards by ranking items according to a specific user-item function, demonstrating that this optimization can be achieved despite the slate nature of the problem. Section: Optimization Algorithm. In this section, we describe the optimization algorithm we use to tackle our problem, starting with a single objective case and later expanding to multi-objective constraint optimization. For single objective optimization, we utilize an on-policy Monte Carlo method that follows two main steps. 1. Training. We create a function approximation for the expected reward based on our policy by separately estimating different components using data collected from an initial policy. This includes approximating the abandonment reward, click reward, and probabilities related to clicks and abandonment. 2. Inference. We adjust our policy to maximize the function we approximated, while still allowing for some exploration. The training data consists of user trajectories, which we store in a dataset. Each trajectory includes sequences of user interactions. We perform gradient updates for our model parameters using specific loss functions in a particular order, starting with the abandonment reward network, followed by the lift reward network, and then the click network. For the abandonment reward network, we estimate the difference between the expected click reward and the abandonment reward. For the click network, we use a cross-entropy loss function to evaluate the probability of clicks based on user interactions. In the inference step, we apply our theoretical framework using the approximated functions and introduce a small chance of promoting a candidate to encourage exploration. When we deal with multiple objectives, we simplify the problem using linear scalarization. We determine weights for each objective and define a new reward function that combines these objectives. We found that it was often necessary to adjust these weights dynamically during training, especially when we made changes to our system, which could slow down our progress. To address this, we update the weights as part of our training process. We apply our algorithm for the lift reward as a vector function for all objectives. During inference, we calculate a set of weights and use a specific ranking formula to evaluate candidates. For offline evaluation, we assess candidates that were randomly promoted during serving. We define a dataset for evaluation and compute the correlation between the combined lift and immediate rewards for each objective. This helps us ensure that our evaluation is less biased by the serving policy. Section Summary. In this section, we present an optimization algorithm that initially addresses single objective optimization using an on-policy Monte Carlo approach, which involves training function approximations for various reward components and modifying the policy based on these approximations. We then extend this to multi-objective constraint optimization by employing linear scalarization and dynamically updating weights during training to enhance iteration efficiency. Section: Optimization with correlation constraint. In this section, we address optimization with a correlation constraint. Using the offline evaluation we defined earlier, we aim to update our weights in the algorithm. Our goal is to minimize the expected value of the squared sum of the product of the lift and the weights, while ensuring that the correlation between the secondary objectives and the primary objective meets a specified threshold for each weight. When we have just one constraint, we can find a straightforward solution. Specifically, the optimal value for the second weight must either be 0 or must satisfy the correlation constraint exactly. This leads us to a quadratic equation for the second weight, which we can solve directly. If there are multiple constraints, we have found that applying them one after the other works effectively in practice. We can also use grid search since the offline evaluation is efficient. Next, we discuss the deployment of the LRF system, which began on YouTube's watch page and later expanded to the home and shorts pages. The LRF system utilizes an on-policy reinforcement learning algorithm, allowing us to evaluate various models using a small portion of overall traffic. This approach enables us to compare both production and experimental models trained under the same conditions. The LRF system continuously learns from user interactions over the past few days, with user satisfaction as our main reward metric. We incorporate user behavior predictions, demographic information, and video features into our model, which consists of small deep neural networks with around 10,000 parameters. The model size keeps inference costs low, and we ensure its quality through offline evaluations before deployment. During serving, the LRF processes the input features to generate ranking scores for all items. To assess the effectiveness of the LRF, we conducted A/B tests over several weeks on YouTube, with results illustrated in our figures. Our primary evaluation metric focuses on long-term user satisfaction. Before launching the LRF, we relied on a heuristic ranking function optimized through Bayesian methods. We fine-tuned two types of hyperparameters for the LRF. Training parameters, like batch size, were adjusted based on offline loss, while reward parameters, including constraint weights, were optimized through live experiments. Initially, we launched a simplified version of the LRF that ranked candidates based on click-through rate multiplied by the lift, using fixed weights for secondary objectives. This version outperformed the previous system by a small margin and was subsequently deployed into production. Section Summary. In this section, we outline our approach to optimizing weights in our ranking algorithm while adhering to correlation constraints for secondary objectives. We demonstrate that for a single constraint, a closed-form solution exists, and for multiple constraints, sequential application or grid search can effectively yield optimal results. Section. Launch Cascade Click Model. In this section, we describe our findings from the launch of the Cascade Click Model. After we initially deployed the LRF, we conducted an experiment to assess the effectiveness of the click model, which involved replacing the click-through rate with the ratio of clicks to the sum of clicks and abandoned actions. We found that incorporating the click model improved performance by 0.66% compared to the control, with a confidence interval of 95% ranging from 0.60 to 0.72, leading us to implement it in production. Next, we explored launch constraint optimization. We noticed that the trade-offs between our main and secondary objectives were inconsistent when we used fixed weights for rewards. To enhance stability, we introduced constraint optimization. For instance, with the same model architecture change, we observed a 13.15% shift in the secondary objective before the launch, while post-launch, this change was only 1.46%, indicating a much smaller fluctuation. We also examined the necessity of the lift formulation by conducting an experiment where we set the abandoned rate to 0. This adjustment resulted in a decline of 0.46% in our top-line metrics, with a confidence interval of 95% from 0.43 to 0.49. Interestingly, the contribution from watch page recommendations increased by 0.2%, with a confidence interval of 95% from 0.14 to 0.26. This highlights the significance of the lift formulation, as merely maximizing rewards from watch page suggestions is not optimal. Lastly, we adopted a two-model approach, where we made separate predictions for the abandoned rate and the click rate. This is referred to as the two-model baseline in our modeling process. The ranking formula we used is the ratio of clicks to the sum of clicks and abandoned actions, multiplied by the difference between the click rate and the abandoned rate. Our experimental results indicated that our production LRF outperformed this baseline by 0.12% in the top-line metric, with a confidence interval of 95% ranging from 0.06 to 0.18.